This is video lesson chapter 1 section 2, linear equations in one variable. If you guys would please grab your notebook. And we need to be all on page 81. We will get started. All right, so first of all, there's three kinds of equations. They're identity, conditional, and contradiction equations. Most of the ones that you guys are used to dealing with are conditional, where there are one or a couple of solutions to them. Identity equations mean that all real numbers will work. So for example, if we had something that started like this, I'm just going to quick sketch one in here. If you were handed an equation like this and you began to solve, we'd distribute here on the left-hand side, and we would end up with a statement that says 2x plus 6 is equal to 2x plus 6. If you guys remember back to the identity property of algebra, this is what it would state, that something is equal to itself. I could take any x value that I want and plug it in there and have it work in that equation. That's an identity equation. All real numbers will work in that situation. A contradiction one, these are the tricky ones because you can actually solve them and come up with a number. But when you go back, you know how you're supposed to go back and check your work. If you plug that number back in, it will in fact end up not working. We're going to take a look at a situation like that a little bit later on in this lecture. So linear equations in one variable are solved by isolating the variable, in other words, getting x alone. Remember, in equation solving, whatever you do to one side of an equation, you have to do to both. You can actually do the wrong thing, and as long as you do it to both sides, you can still recover. So if everybody would go with me to the bottom of page 83, we're going to do checkpoint number 2 that's there. Okay, so on the screen here you can see the equation and notice that it does match the one that's at the bottom of your book there. So let's take a look. To start solving this one, we're going to distribute. So 4 times x and 4 times 2. Distributing on the right side as well, 5 times x and 5 times negative 6. Whoops. 5 times negative 6. Now we start to simplify if possible. I can combine that 8 and negative 12, so I'm going to do that next. Bring your variables together. I'm going to move the 5x to the left side. And then I'm going to move the constant to the right side where the other constant is. And then in solving this one, I still need to divide away that negative 1 that's in front of my variable. And we get 26 for a solution. Remember, when you're solving with equations, you should be able to put it back in and check yourself. It's the only way to tell also if we end up with one of those contradictions equations. So I do suggest that you give that a try. If we do that here, if we put 26 in for x, we're going to get a 4 times 28 minus 12 and a 5 times 20 on the right. If we had 26 minus 6 over there. 4 times 28 is actually 112. And you can see that 112 minus 12 is going to match that 100, so our check works. 26 is in fact a valid solution. Solving rational equations. What does that mean? Well, remember, rational numbers are anything that can be placed in fraction form. So a rational equation is going to have some rational expressions in it. So in other words, you're going to get some fractional expressions inside your equation. Adding and subtracting fractions, recall, you have to have the common denominator. Once in a while, or actually, generally it's the way I think I go at them most of the time, I like to get rid of the denominator. So take a look at the example that I've given to you. This one, I believe, is checkpoint number 3 on the next page, on page 84. All right, so take a look at your denominators right now. We do have additions and subtractions in here. I need a common one. So far I've got 9s and 3s and a 1. So if I were to multiply everything in this equation by a 9, I could eliminate every single denominator that I have. So on this first term, if I multiply by 9s, I'll be left with 4x. Next term, I can reduce a little bit. I end up with negative 1 times 3. In the x term, 9 times x will just leave me 9x. And in the last term, I can do a little reducing again and end up with 3 times 5. And now I just solve like always. Move my variable term to the left. Constant to the right. Divide by negative 5. X is equal to negative 18 fifths. Again, we probably should put that back in there to make sure that it does check through. It will. Okay, so this is in fact is a valid solution. So here comes that slide that I was talking about with that extraneous solution stuff. When you're done solving an equation, you really should check to see if the answer works. If it doesn't, it's called extraneous, and they do happen. Look at example number 4 at the bottom of page 84 with me. Look at their solution there. Okay, they come up with x equals negative 2. All of those steps are valid. They haven't made any mistakes. That 4x is equal to negative 8 turns into x equals negative 2. But if you were to put a negative 2 back into that starting rational expression, look what would happen with the second term. You guys see how there is a 3 over x plus 2? And if you put that solution into that particular fraction, you're going to get 3 over 0. That is an irrational fraction. That is an irrational statement. You can't have it. It's undefined. That's what throws the negative 2 out. It cannot be a solution. And so there are truly no solutions to that expression. All right. There is a checkpoint underneath that one on the bottom if you want to go through it too. Remember, you can go to that, was it larsonprecalculus.com, and it'll walk you through another solution of that. Intercepts. We talked about intercepts a little bit already with our first lesson. Finding intercepts is something that we do often because they are helpful in graphing. They are also solutions for some of our graphing. Notice or remember that to find the x-intercept, you're going to plug 0 in for y and solve. To find the y-intercept, you need to plug 0 in for x and solve. So let's give this a try. If we had this linear equation, y equals negative 3x minus 2, the x-intercept is found by putting 0 in for y. Solving, I'm going to move my constant and then divide by the coefficient. So negative 2/3 is equal to x. Now that's not my intercept. An intercept is a point. So together these two things, the 0 that you plugged in and the x value that you get out, form your intercept. So my x-intercept is the point negative 2/3, 0. Do not simply put x equals negative 2/3 as your intercept. Y-intercept, let's do that one. To find the y-intercept, you put 0 in for x. Now, most of you guys probably can see the y-intercept in this particular one already because we're used to graphing slope-intercept form. But by putting 0 in for x, y equals negative 2. Do you guys remember how on y equals mx plus b, b is your intercept, which is what we just found as well. Okay, so you might have seen that without the actual plugging in of 0. Regardless, let's come up with our actual answer yet. Y equals negative 2 is not an intercept. It's half of it. Together with the 0 you put in for x, it makes the intercept point. Okay, so list your intercept answers as coordinates. Give me the whole ordered pair. All right, so that's it for today. Your assignment, we're working problems on 87 to 89. Okay, like as always, try the first odd one or even one in a section. If that goes well, jump towards the end and do a harder one. If that section looks good, you can move on. So nothing to turn in for tomorrow, but don't skip, especially the rational equation ones. Do a lot of those equations that have fractions as parts of them. If you have any questions, we can go over them tomorrow in class.